Hello everyone, my name is Sushant Saraswat. I am pursuing my MS in Data Science from Ljmu. Over the next few minutes, I will be presenting my PowerPoint presentation elaborating the study I have undertaken as part of my MS thesis titled Evaluation of Human Pose Estimation for Yoga Practices Using Computer Vision. The flow of my presentation is as follows. I will be commencing with the introduction, followed by the motivation behind taking up this study. Thereafter, I will present the problem statement, aim and objectives of the study, literature review undertaken by self, methodology adopted during the study, toolkit used during the implementation, including both hardware and software, a brief on the YOLO V8 pose algorithm, the architecture used to effect the implementation, results and discussions, a brief demo of the implementation on an open source as well as real-time streaming video, conclusion, and finally the future recommendations. Commencing with the introduction, most of us are well aware of the positives of yoga practices, which hold a significant and transformative influence on the health of the practitioner. Yoga involves executing a series of intricate postures, which are termed asanas. It is imperative to execute these poses precisely to accrue maximum benefits. It is recommended that these asanas are performed under the supervision of a qualified instructor. A short brief into what motivated this endeavor. I am an avid yoga practitioner since it helps me in keeping myself physically and mentally fit. However, during the busy schedule, it is not always possible to seek active feedback from an instructor. When I was researching to find a solution, I came across a fact that globally, the obesity rates have been tripling every decade due to people not working out. This germinated in me the idea to tackle the issue not only for myself but also for all those other yoga practitioners who want to benefit from the same without the physical presence of an instructor. Coming to the problem statement, achieving precise body alignment is crucial during the performance of the asanas, which can be a challenge for the enthusiasts. To practice yoga independently requires an effective feedback mechanism. Earlier solutions like wearable tech and pose detection hardware tools like Microsoft Kinect have proved inefficient since they are maintenance intensive and obstruct the movement of the practitioner. With the advent and progress of computer vision in recent years, especially in the domain of human pose estimation, it has become a promising option to devise a solution for providing feedback to yoga practitioners. However, human pose estimation has its own associated set of challenges such as occlusion, different body shapes and sizes, dynamic movements, etc. The aim of this study was to evaluate human pose estimation in yoga practices using computer vision. The objectives were as follows: to implement the recently released YOLO V8 pose models with transfer learning on yoga dataset, to accurately estimate the key points and skeletal structure in yoga poses, to develop a Keras model to classify real-time yoga asanas via webcam, and to assess model performance based on training and validation accuracy and loss parameters. Literature review. A comprehensive review of over 50 papers was conducted by self as part of this study. Since human pose estimation for yoga is a niche domain with very few papers, the review was extended beyond yoga applications to include those domains as well which could guide during the endeavor. It emerged that the human pose estimation has evolved significantly over the past few years, primarily due to advancements in computer vision and deep learning. Additionally, it was also ascertained from the literature survey that pose estimation indeed aids in yoga by analyzing and correcting the postures of the practitioners, thereby affording maximum benefits. As recently as 2022, a significant thrust has been made on involving modern deep learning techniques since the earlier methods being used in the domain were lacking accuracy. During the literature survey, the use of YOLO, which stands for You Only Look Once model, seemed to exhibit promising results in the field of human pose estimation. Additionally, earlier studies also emphasized upon use of augmentation techniques to balance imbalanced datasets to enhance model robustness and diversity. Unbalanced datasets, on the other hand, proved challenging. This combined, along with the issues such as model overfitting, real-world deployment, clothing, environmental variations, etc., made the problem more challenging. When this study was conceived, YOLO V8 pose models were just released in Jan 23, and there existed no precedence of these models being employed in yoga pose estimation. Thus, this study can be considered a maiden effort using the YOLO V8 pose model in the domain of human pose estimation for yoga. I will now explain the methodology of how this study was planned. An open source yoga image dataset having images of different asanas was planned to be sourced for this study. An exploratory data analysis was to be undertaken on the dataset. Special attention to class imbalance checks were planned to obviate the challenges associated with such dataset. In case of class imbalance, class balancing was to be undertaken to reduce bias with the help of data augmentation. Thereafter, key point detection was to be performed on each dataset image using YOLO V8 pose algorithm. These key point coordinates were then to be normalized and saved in CSV format. The dataset so generated would then be split into training and validation datasets. A Keras model would then be developed using the training dataset for classification of yoga poses. The validation of the Keras model would be undertaken on the validation dataset, and finally, the model so generated would be evaluated on the basis of accuracy. Before we proceed any further, I would like to showcase the toolkit which I employed during the implementation. In hardware, I employed a system with x64 architecture having an Intel CPU i7 core operating at 2.4 GHz, 8 GB RAM and 500 GB of storage. For software, I used a 64-bit Windows OS with Python version 3.9 and Jupyter Notebook. Additionally, Keras, NumPy, Pandas, TensorFlow, Matplotlib, ITR tools libraries were used for their respective functions. OpenCV library was used for computer vision and Ultralytics was used for employing YOLO V8 pose algorithm. A brief on YOLO V8 pose algorithm by Ultralytics. YOLO is a comprehensive state-of-the-art computer vision library which can undertake classification, detection, segmentation, and post-classification. Its latest post-detection algorithm was released in its 8th version in Jan 23. The algorithm can extract key points from its predictions in real time and its performance is good. The key points are essentially x and y coordinate values. Here, on the left hand side, we can see the key points on a human figure that YOLO V8 can predict. The total number of such key points on a human are 17, starting from 0 to 16, and covers all the major joints in the body. The YOLO V8 algorithm is trained on COCO Pose 2017 dataset, which contains 2 lakh images labeled with key points for pose estimation tasks. The YOLO V8 pose algorithm has 6 models to cater for various computational scenarios as shown in the table. Coming to the overview of the architecture used for the implementation, the yoga pose dataset was used in its original unbalanced form as well as in the balanced form post data augmentation as displayed. The 6 YOLO V8 pose models were used by transfer learning on both these datasets, resulting in 6 CSV files, each for imbalanced and balanced datasets. 3 Keras sequential models were devised and each of these were applied to the data in CSV files of both imbalanced and balanced datasets. This resulted in 18 combinations for imbalanced and balanced datasets each, resulting in a total of 36 combinations that were assessed for their performance. Diving deeper into each component of the implementation now, the yoga dataset was an open source dataset sourced from Kaggle. The dataset had 47 distinct folders, each representing a particular yoga asana class. Each folder has yoga pose images pertaining to that asana. A schematic of the dataset is displayed on the left hand side. The dataset size was approximately 500 MB in size and consisted of about 2750 images of various yoga asanas. Here, we can see a glimpse of few images of the yoga asanas on the left hand side. On EDA, it was observed that the classes were imbalanced, with the least number of images in an asana folder being 12 and the maximum being 96, as seen in the top graph on right hand side. This would have resulted in a bias in the performance of the model. In order to obviate the issue, data augmentation was employed to increase the number of images by generation using techniques like flipping, skewing, etc. And this resulted in equal number of images in all yoga asana folders. Coming to Keras sequential model, three different Keras sequential models were developed and tested on the datasets. The primary reason for the generation of multiple Keras models was due to the observation of overfitting in the first model with hidden layers. To obviate the issue, the number of layers in the subsequent models was reduced. The first model had an input layer of 512 neurons activated by rectified linear unit ReLU, followed by 256 neurons also employing ReLU activation, and the final layer having neurons equivalent to classification categories, that is 47, and employing softmax activation. The second model had an input layer of 512 layers activated by ReLU function, followed by a final output layer of 47 neurons having softmax activation. The third model was similar to the second model, with the only difference being in the reduction of input layers to 64 only. A brief on the hyperparameters. The number of epochs used were 200 and batch size for training was limited to 16. Softmax was employed to obtain probabilistic output for each asana class. Adaptive moment estimation or ADAM optimizer was used for its adaptive learning rate for each parameter, thereby enabling faster conversions during initial phases of training, resulting in quicker progress and reduced likelihood of getting stuck in suboptimal regions of loss landscape. Categorical cross entropy loss function was used since it is effective for multi-class classification tasks. It measures the dissimilarity between the predicted probabilities and the actual class labels, guiding the model to minimize the divergence between them. The categorical cross entropy is particularly well suited for scenarios where the output is mutually exclusive and each sample belongs to only one class. Early stopping callback was used to monitor the validation accuracy during training and halt the process if no improvements were observed over a defined patience period. This helps in preventing overfitting and curtails excessive training. The following table was generated post-performance evaluation for the imbalanced dataset. We can see the 6 YOLO V8 pose models on the left hand side and 3 Keras models on top. For each model, the model accuracy and validation accuracy has been derived. It is observed that the performance of the combination of YOLO V8L pose algorithm along with second Keras model was the best amongst all the other in terms of accuracy. The model accuracy was 97%, whilst the validation accuracy was 86%. The graphs for the YOLO V8L model for the 3 Keras models are as displayed. The x-axis denotes the number of epochs, whereas the y-axis denotes the loss or accuracy. The blue line represents the model loss, the red line denotes the validation loss, the purple line denotes the model accuracy, whereas the green line signifies the validation accuracy. As discussed earlier, the model in the center employing the second Keras model was found to be the most suitable in terms of model and validation accuracy. Similarly, the performance accuracy for balanced dataset was also determined. Here also, the combination of YOLO V8L pose algorithm along with the second Keras model produced the best accuracy results. The model accuracy was 97%, whilst the validation accuracy was 84%. Similar graphs for the balanced dataset for YOLO V8L pose algorithm along with 3 Keras model are displayed, of which the center graph represents the best case. Coming to results and discussions for model performance for imbalanced dataset, the bar graph on the left hand side displays the performance of the 6 YOLO V8 pose models for the model and validation accuracy. It was observed that the larger models exhibited improved model and validation accuracy. The model variants achieved consistent accuracy between 87% to 97%, which is considered good and showcases robustness in pose classification. The validation accuracy in each case was observed to be slightly lower than the training accuracy, with YOLO V8L and 8X models exhibiting better generalization. YOLO V8L was observed to outperform other variants in accuracy. Close alignment of the validation and training accuracy affirms good model generalization for unseen data. This is especially important for real-world deployment. However, as a flip side, large models, though offering higher accuracy, demand more resources. This necessitates a balance between accuracy and complexity. Results and discussion for balanced dataset. It was observed that the dataset augmentation increases model and validation accuracy for all YOLO V8 models and Keras architecture. Denser architectures were observed to capture intricate patterns, which was evident in superior YOLO V8 variant performance. Less complex architectures display respectable performance, showcasing model complexity efficiency trade-off. YOLO V8L post model outperformed other YOLO V8 variants in this case also. Validation accuracy was observed to follow the accuracy trend, indicating good generalization. Reduced gap suggests data augmentation's role in mitigating overfitting. I will now showcase the demo of the implementation of the developed model on an unseen open source video. The custom AI model is trained on Yoga 47 open dataset. Here, the AI model is running on an unseen video which has been sourced from YouTube. The pose classification and probability is displayed along with key points, and skeleton is generated automatically. The AI model can be customized for analyzing various sports with an appropriate training. This can help the sportsperson to review and improve their performance. Additionally, other domains where human pose may be detrimental can also be used for specific use cases. So what are the inferences which can be drawn from this implementation? To begin with, the yoga poses were accurately classified despite occlusion and intricate background. Despite very subtle discrepancies between certain yoga poses, the model could still differentiate between those asanas. The model could perform well despite unconventional limb orientation such as feet above head level, etc. And the model generated differentially colored bounding boxes for distinct yoga asanas, facilitating ease of identification along with display of class probabilities. We will now see an implementation demo on real-time streaming video. The following can be inferred from the demo. The model could perform accurately for multiple individuals simultaneously. Despite distinctions in the gender, height, and other physical attributes of the subjects, the model worked seamlessly. The model's performance was unperturbed by the dense environment, for example, bed edge on the lower left-hand side and the book rack on the lower right-hand side. Coming to the conclusion, the results, discussions, and demonstrations clearly indicate the successful development of a robust pose estimation pipeline using YOLO V8 pose models and Keras classification. The developed methodology and empirical insights provide a very strong foundation for pose estimation research. All the stated objectives indicated during the beginning of the study have been achieved. These include implementing recent YOLO V8 pose models with transfer learning on yoga dataset, accurately estimating key points and skeletal structure in yoga poses, developing a Keras model to classify real-time yoga asanas via webcam, and assessing model performance based on training and validation accuracy and loss. Finally, we'll take a look into some future recommendations. Advanced techniques like GANs can be used to further enhance model performance and generalization. Integration of image and depth data can be explored for improving pose estimation accuracy further. Research can be undertaken on improved sampling strategies and domain adaptation methods to address real-world pose estimation challenges. And last but not the least, the deployment of the model on edge devices can also be investigated. With this, I come to the end of the presentation. I hope I have been able to complete all significant aspects of my study. Thank you for your patience.